I'm very pleased to introduce Bernd Schroers, who's from Heriot-Watt. He's a professor at Heriot-Watt. I think he's a fellow of the Royal Society of Edinburgh. And I think I'm right in saying you were probably one of the last people to collaborate with Michael. So tell us about the time in Edinburgh. Thank you.
Thank you. Thank you very much. And also for the invitation to speak here. It's a great honor. People often say that the post-lunch talk is one of the hardest to give, but I think the organizers have created a new category, post-drink reception talk. So I think the best to entertain and educate and inform in equal measure. So this talk is about the time Michael spent in Edinburgh from 1997. He was professor, and during that time he was also president of the Royal Society of Edinburgh, and he kept interacting with the entire world, but of course, in particular with some people in Edinburgh. So we had the great fortune of being able to talk to him, interact with him, learn and develop ideas. So I will share some memories and also some of the ideas. So I will talk about some mathematics and physics, picking up on what Robert Dycroft mentioned at the end, the exponential growth. Michael really didn't slow down. There was a constant generation of new ideas, and so I will reflect on some of those, and in particular in the way in which they combined physics and mathematics, which I think is a very interesting topic in itself in Michael's life. So that's one aspect I particularly want to focus on. So I'll begin with some pictures. So these are just, looking back at my laptop and pictures I took at various points. And Roger Penrose was a regular visitor, an old friend, of course, of Michael's, and he would visit regularly, and this is in 2017. I'm sure Michael would be absolutely thrilled about Roger winning the Nobel Prize. Last year, that would be amazing news. And so this is one such visit, and another person that's, I'm not going to introduce everyone on this picture, but Andrew Ranitsky, and next to Roger Penrose is another person who features in many of these pictures, and who is a professor at Edinburgh, was also, in some sense, the kind of mathematical living room. His house was the mathematical living room of Edinburgh. So Andrew himself passed away before Sir Michael, but they're both in this picture. This picture is taken in a restaurant which was also a kind of mathematical living room. It's the restaurant called Beirut. It's a very good, but very simple but excellent Lebanese restaurant, very close to the ICMS new location. You just walk across the road, and that was a popular location. And Michael was always greeted like the king that he was there. So they recognized obviously his Lebanese roots, and they recognized he was an important person, and they loved having him as a guest. And Michael loved going there. It was very good food, and he knew all the dishes. He liked their wine. And again, Michael, as you all know, wouldn't stop wine from discussing mathematics. So he would have no problem with filling a discussion like the one we're about to have, with lots of mathematical details and new ideas. And that's exactly the spirit in which you are taking part with your glasses of wine in front of you, even if I have to stick to water for now. So, I mean, I mentioned, of course, Michael's father was Lebanese, and Michael's mother was Scottish. So living in Scotland and eating Lebanese regularly was very much his way of also celebrating his heritage. That's another picture from the same visit. This time we also have Oliver Penrose, colleague of mine at Heriot-Watt, the far end of the picture. That's another dinner party. I think that was actually a birthday event, but that's again Andrew Ranitsky in front. So these are literally just random shots. I was looking through my picture collection and I found these. That's Michael at the Heidelberg Laureate Forum, where he was a regular guest. So this is an event that happens every year, where prize winners in the computer sciences and fields medalists and prize winners in mathematics are invited to interact with promising young students in mathematics and computer science from across the world. And Michael loved going there. Again, you can see him holding court at this reception, and the whole table is listening with rapture. I thought I'd bring this in as well. I mean, because Michael had strong views in everything. He had a strong taste. He had strong political views as well. He was president of the Pugwash Confederation, and he fought for nuclear disarmament all his life. he also had views on Scottish independence. So when the referendum happened, he wrote an article in the Times where he explained why he was in favor of Scottish independence. And he mentioned in particular two reasons, one to do with the Trident submarines, which are based in Scotland. The other one with him foreseeing that Britain would leave the European Union and thinking this was one way of at least assuring that Scotland would stay. Was it part A we came through and part B we will find out. But it's typical that he would not hold back from putting that into print and explaining it in some detail. Sorry, that's the wrong way. I'm going back in time. So these are pictures I found from Nick Manton's 60th birthday celebration here in Cambridge. And I'll come back to some physics that Nick Manton and Michael Atiyah developed together. And I think the last picture I have is again going back in time. This is a picture taken at Harriet Watt University with students who had come to Scotland, having been at one of the Ames institutes across Africa, the African Institute for Mathematical Sciences, which when Michael heard about it, instantly inspired him. He was very, very keen to support this initiative. So this was an event where we talked to the Scottish government to give us some funding through the Scottish Funding Council, which materialized. So over a period of 4 years, there was funding for Scottish lecturers to attend one of the, or to go to one of the Ames institutes across Africa to teach there. And Michael's support was very important in making that happen. So that was my picture collection. I also wanted to talk about, in the context of physics, three names which are very prominent in historical terms for Michael's interest in physics. And one, of course, is Maxwell, James Clerk Maxwell, the local hero in Edinburgh, and the inventor of gauge theory, even though he himself wouldn't have realized that, and of Lorentz symmetry. Because Einstein's paper on special relativity refers explicitly to the electrodynamics of moving bodies. That's the first relativistic theory written down without realizing that it had that property. And the statue there of James Clerk Maxwell was erected just outside the Royal Society, but that was an initiative by Michael Atiyah. So he initiated, as president of the Royal Society, that Maxwell should have its statue in Edinburgh, and it duly happened, as it often did when Michael set his mind to something. So that's still there. So actually, so the statue is about to be moved a little bit down the road because they are reorganizing the street on which it is, but it will remain in the central location on St. Andrews Square. So that's permanent. Then the other figure, not surprisingly, that Michael often referred to is Albert Einstein when he talked about physics. And there's I explained in some detail what particularly he connected with Albert Einstein, but one, of course, is the geometrization of physics. So writing down a theory of geometry, which is gravity, is exactly the kind of theory that Michael was always interested in his own research, but also in physics. And I think another aspect of Einstein that he felt connected to is that Einstein has, in some sense, two faces. We know him as a brilliant young physicist, where he invents special and then general relativity and quantum theory, and to a large extent with work on stimulated emission and the photoelectric effect. And that's what he's best known for in physics, but then also as an older scientist, working on unified field theories and not getting the recognition that he perhaps expected. And Michael connected to that to some extent, being recognized for what he had done as a young mathematician, but not for what he was trying to do in older age. And equally, the same is true for Dirac, who also is somebody that he often referred to, and who also is celebrated for work he did as a young man, and viewed more critically for work he did as an older man, when he was interested, for example, in the role of large numbers. So that's the work of Dirac, which is interesting, but has a different status, certainly, than the Dirac equation. I come back to their philosophy later, but these are the names I think which are important to understand Michael's interest in physics. Fourth in that list is Hamilton. So Hamilton is somebody he came back to a lot, not least because of the quaternions, which Michael referred to frequently in various contexts, and because Hamilton was actually the first to write down the Dirac equation. which Michael was very aware of and often mentioned. In actual physics collaborations, there's many people I should mention, and I should instantly apologize. There's an international, worldwide audience, and there's people here, many of whom have worked with Michael in various situations, and I can't give a full description of the collaborations that have happened. But again, just based on my picture collection, and I think also with some fairness of the relative role, I think it is fair to show a picture of Ed Witten, with whom Michael worked, and also with whom he mutually educated about physics and about mathematics. So this is one person from whom Michael learned a lot of the physics that interested him. That again is a picture with Andrew Rowanitsky at Andrew Rowanitsky's house in Edinburgh. And Nick Manton, who taught Michael, I think, a lot of the physics that interested him, and worked with him on a number of specific projects related to physics. And again, I'll mention those and discuss them in a little bit of detail in a minute. And that picture is again taken at Nick's birthday that I showed earlier. So I've found it quite helpful to divide the discussion of Michael's interest in physics into two periods. And I've called them the inadvertent and the intentional physicist, because it is very striking how Michael's early work is incredibly influential in physics without him having any interest in physics whatsoever. And he makes that very clear. And I agree with Nigel, it's very interesting and rewarding to read the prefaces that Michael wrote for his collected works. In them, he explains how he was thinking at the time, at least how he remembers thinking when he was writing the collected works. And he makes some very interesting comments about that time. So he starts off, for example, in volume 4, which is the second on index theory. He says, my knowledge of physics was very slim, despite having attended a course in quantum mechanics by Dirac himself. And I was discussing this with various people in the room earlier, this question of whether Michael actually knew the Dirac operator or Dirac's operator when he discovered it with Michael Singer. I think to some extent he didn't. So the work leading to the index theory was done without realizing that there is a physics world out there where the Dirac operator already plays a role. That's certainly how it comes across from my reading. But I should also say, one should probably see this in context, because in the same preface, Michael says, my analytical background was very weak, and I remember having to be instructed in the significance of the Fourier transform. So Michael is being very modest here about his knowledge in both physics and in analysis. And that is in the preface to the work, which then that's the index theorem. This is a picture that was made for the 80th birthday celebration. And it is kind of striking to think this came out of mathematics when, as Robert said in his talk, every single part of that equation would now be seen as basic field theory physics. There's the Dirac operator, there's spinors, there's sections of vector bundles, there's a metric, and there's a connection, and they all enter this formula. And to think that this could come out of work which wasn't looking at physics is really quite extraordinary to my mind, looking back at this. And Michael himself commented on that. So he said in his preface to the, again, to the index theory 2, I would have been extremely surprised if I had been told that this work would in due course become important in theoretical physics. I think reading that now is really quite astounding, because it's physics all over. And there's a similar comment. I'm really quite struck by the way most of the work with Singer and I did in the 60s and 70s has become relevant to physics. So so 60s and 70s is still a time when Michael, I think, has no particular interest in physics, from what I can see. He then gets interested in the instanton equations, so self-duality equations, and finds this solution, the ADHM instanton construction. And that's, to the physicists, a real surprise, which Polyakov summarized by saying that was the first time abstract mathematics has been of any use. That's I think, slightly question whether that's really been said, but that's something that Michael cites and that he likes very much. But of course, that work set the foundation for all kinds of exciting developments in gauge theory that Michael was involved with. One of them is monopoles. So that is the self-duality equations in 3 dimensions, which you might superficially think would be easier, but actually is quite a lot harder than the instanton equations. And the idea that you can study the dynamics, the time evolution of these monopole fields by looking at geodesics on modular space, equipped with a natural metric. So that's when his interest becomes more active, but he's still in the same volume 5 says, from 1977, my interest moved in the direction of gauge theories and the interaction between geometry and physics. I had for many years had a mild interest in theoretical physics. So it's still, it's sort of underplayed. It doesn't seem to be the main interest that he had at that point. So I think that really changes. And so in the second half of what I want to say, I would like to talk about some research that Michael did, which really is addressing physics questions head on. And by physics, I really mean observable facts of nature and trying to describe them in terms of a mathematical model. Because there's a, physics is not necessarily what physicists do. There's a lot of physicist discussion which aren't directly related to reality and modeling reality in terms of mathematical descriptions. But Michael became interested in doing precisely that. And how he did that, I think, is also interesting. And we had, it was Nina's talk, I think, where we had a list of how mathematicians and physicists might interact, but it didn't include this particular approach, which is often credited to Dirac. The idea that you might use the resources of pure mathematics in an attempt to perfect and generalize the mathematical formalism that forms the existing basis of theoretical physics. And after each success in that direction, you try to interpret the new mathematical features in terms of physical reality. That's an approach which I think Michael approved of and which he often used. You take the existing mathematics, which is already used in physics, but you try to understand it and push it further. And then you ask, is it physics? Rather than taking the model and trying to construct a model for an open physical problem. So that, of course, is that's been widely quoted, but I think Michael operated in that way when doing physics. And there's another paper which I know from discussions which Michael just read in great detail and repeatedly, which is the paper by Einstein and Rosen. So this is a paper written in 1935. Very much part of a period where Einstein was interested in unified field theory, and where he describes the idea of using field theory solutions, non-singular solutions of field theory for describing particles and their motion at the same time. So I'll read this out because I think it's quite an important quote to sort of understand what Michael got interested in. So complete field theory knows only fields and not the concept of particle and motion. For these must not exist independently of the field, but are to be treated as a part of it. On the basis of the description of a particle without singularity, and as the possibility of a logically more satisfactory treatment of the combined problem, the problem of the field and that of the motion coincide. So the idea is that you have this partial differential equation which has solutions which are non-singular, and by solving and understanding that partial differential equation, you understand the structure of the particle and you understand how it moves, because it's all part of the solution of a PDE. And that approach is what we might now call the soliton description of matter, to describe matter in terms of solitary wave solutions of particular field theories that allow for them, that allow for stable solutions. And so this paper is one that Michael liked and often went back to and got inspiration from. And there's another quote of Einstein's that he was very interested in, and I was keen to find out whether it's actually true. And it's the quote, it would be quite enough to understand the electron, which Einstein is said to have said when being told about all these new particles being found in the 60s and 70s, pions and all the delta resonances and all kinds of things were discovered, and the picture of field of particle physics got so complicated that Einstein says, this is all, I don't believe any of it. It would be quite enough to understand the electron, because he didn't believe or understand the quantum theory of the electron. He didn't think that was the right description. And so I put Michael Atiyah in touch with a historian of science, Jeroen van Dongen, who had written about this, and they conferred and discussed this. There's no definite place where Einstein is known to have said this, but it's consistent with lots of things that he did say. So it's that's the approach that Michael took up to that. So an example of a modern field theory, which is in that spirit of the partial differential equations without singularities, describing particles in their interactions, is the Skirm model of nucleons. And these are pictures taken from the book that Nick Manton and Paul Sutcliffe wrote on the subject. And this is where Michael really became actively interested, very much, I think, in interaction and guided by Nick. And so they wrote a paper where they used ideas from instantons, from SU Young-Mills theory, to construct Skirm fields. Okay? So this is very much flowing on from its interest in gauge theory, but it's really addressing a problem that is designed to give us some insights into nuclear physics. How you describe the moduli of several nuclei interacting. And having an understanding of moduli is important. If you want to do physics, you need to understand not just the solutions, but also a family of solutions to do quantum theory. And so this is something I did with these instantons, again, with Nick. You can then start to begin to look at deuterons. So this is a deuteron picture, actual physics, and modeled by instanton-generated Skirm fields, and then quantized. And I'm just showing that because I think it's an example of Michael working in a direction which really begins to connect with real physical questions. There's another problem which occupied him a lot in his Edinburgh years is the question of the configuration space conjecture, which came out of physics, was put to him by Michael Berry. So this, of course, is a Sir Michael B and Sir Michael A story, where in the context of molecular or atomic physics, Michael Berry was interested in a map from the configuration space of n points in Euclidean space into the unitary group modeled out by the torus, which should be equivariant with respect to the action of rotations on both sides and of permutations. So that was the problem that was posed, and it came out of a real physics context. It had to do with understanding spin states of high charge atoms. And Michael gave a very explicit proposal for how to do this. And it involves a thing called the Majorana stellar representation. So what you do is you look at the n-1 particles from one particle, and you project the lines onto the sphere, and you write down a polynomial that has zeros precisely of those n-1 points. That way you get from n points to an n-dimensional vector space, a space of polynomials of degree n-1, and the conjecture was that would be independent. This would be independent, that would provide a basis after unitarization and gives you an UN matrix in this way. And naturally, you would not have the phase because the polynomials that you get would only be defined up to a multiple in any case. So that's a very concrete question, and that became in itself a conjecture which is now studied, and Paul Sutcliffe and Michael pursued this and sharpened it. But what I find interesting is that Michael took this out of atomic physics and then started thinking about it in new ways. So he was interested in the determinant of these polynomials and what equation it satisfies, if that's related to a Schrödinger equation, if that's related to entropy. So he started throwing these physics ideas around and trying to move with that. Another proposal that came out of that time is a proposal with Greg Moore about how to combine the notion of special relativity, which has no length scale that's invariant, with the requirement of quantum gravity of having a discrete length scale, the Planck length. So how can you have a theory that's relativistic, therefore shouldn't allow for a length scale because relativity doesn't respect length, and at the same time has a Planck length? And Michael's solution, I think, is wonderful, and this paper, to my mind, hasn't been studied enough. He suggested take the Dirac operator and exponentiate it. So it's a kind of finite difference operator in the way that you might in one dimension, that would be straightforward. And if you take the Dirac operator and exponentiate it, you get a finite difference operator, which is relativistically invariant. And in fact, our discussion started because these operators arise in quantizing 2 plus 1 dimensional gravity. So that precisely this kind of thing does occur, and Michael was interested in that. But we never worked on this. The one thing that we did work on with Nick and also Jose Figueroa O'Farrell is Michael's idea to describe particles in terms of 4-dimensional geometries. So this takes an old idea, the Kaluza-Klein idea, which is the idea that you combine electricity with the geometry of gravity into a higher dimensional theory by taking a circular dimension to account for electrodynamics. That's an old idea, but the idea here was to use this as a model for particles. So you look at 4 manifolds, which are asymptotically fibered, but the vibration breaks down at a particular point, and where that happens, that's where the particle is. So you get a picture of the particle, and at the same time, it's embedding into a 3-dimensional geometry, which is fibered by a circle with a circle vibration over it. So that was an idea which came out of the idea of these Stern fields, which are 3-dimensional fields, having come from 4-dimensional gauge fields. So that was intimately connected, and it uses the idea of Kaluza-Klein, but it dualizes it because the twist in the vibration, in this case, has to be interpreted as an electric charge, not a magnetic charge. But the basic idea is to get all the quantum numbers, electric charges, lepton number, baryon number, from the topology of the 4 manifold, and to use the Dirac operator to connect to spin. So that was all of Michael's ideas in this picture. And we explored this, and this is not the place to go into any detail, but I still learned a lot from that discussion. I think some of that is very interesting. So the proposal was manifold Taub-Napp to describe an electron, and the Atiyah-Hitchin manifold to describe a proton. Now, there's all kinds of things that you have to instantly follow up if you say that. But there's a couple of things which I still like about this. If you want to describe a point particle by a smooth geometry, then the Taub-Napp manifold is one way of doing that. Taub-Napp has a circle that the vibration breaks down only at one point, and that's where you put the particle. It gives you a way of understanding spin-a-half being connected to charge 1. It's a very interesting way, which Michael liked very much, that Taub-Napp near the origin is C2, that which is the spin space of an electron, and asymptotically it's R3 with a tiny circle vibration over it. And the way that gets interpolated always fascinated him, and he thought about that a lot. The other manifold, the Atiyah-Hitchin, is the other solution of the same equation, the self-reality equations in 4 dimensions, which are SO3 symmetric. And that you should get 2 solutions of the same equation with such different properties, one looking like an extended particle, the other one like a point particle, again, fascinated him. And I should say, even though that certainly hasn't revolutionized the standard model, it has led to interesting geometry, because you can then ask, how do you combine these particles into multi-particle situations? And Michael Singer and I followed that up with a geometrical discussion. So it's not physics, but it's definitely interesting geometry. I'll have listed here to wrap up what I think are themes in Michael's thinking about physics. Beauty is important, and you should follow the great minds. So he definitely read his Einstein and Maxwell and Dirac very carefully. He didn't believe quantum mechanics as it stands could be fundamental. It's too linear. He actually liked Bohm's theory, which again I know is a controversial proposal, but it's something that he kept coming back to. Gauge theory to him there was too much choice. Nick asked the question at the end of Robert's talk about there being particular gauge groups that you have to choose. To him, to Michael, that was too much freedom. That there shouldn't be that choice. You shouldn't have to pick in a fundamental theory. String theory was an important part of the story, but I don't think in his thinking he never wrote about string theory on its own. That was the core to the answer. And the central role was geometry, nonlinearity, and 4 manifolds often came back. Division algebras often also came back in the speculations, particularly in the last 10 years. And the Dirac operator serves as a bridge between that geometry and the linear spaces that you need to describe quantum mechanics. After all, that is a linear theory. And intuition beats data. And I can't resist repeating one discussion I had with Michael when I said, look, physics has a lot of data, and you have to get that data right. You can't just pretend it's beautiful, therefore this theory is correct. And Michael kept arguing against this, and I said, look, what you're saying is just a gut feeling. But he thundered back and said, this is my gut. And to him, that settled it. I can't, again, this is speculation, I'm not a historian, but I think his experience of having inadvertently had this incredible impact on physics without thinking about it, as a younger man, gave him great confidence that what he thought in his mathematical gut would ultimately turn out to be important in physics. There was a great confidence that he couldn't go wrong. Just to final two words, I think it's important to acknowledge that Michael was, for so many of us, a wonderful teacher, and the books he wrote will remain, I'm sure, an inspiration and a bridge between mathematics and physics. So these are some of the books that many of us studied, and it made abstract mathematics accessible and used the language of physics for the mathematicians in a wonderful way. So I think these books and other publications that he wrote played a big role in bridging that gap that had broken down into the 70s, and it was rebuilt to a large extent, I think, in Michael's teaching. And final picture that I chose is a picture, a juxtaposition of two people which in many ways had a similar role, I think, in the interplay between mathematics and physics. And again, there's a much bigger story here that I'm not qualified to tell, but I like the way they both incline their heads at the same angle. And Michael often said that wherever he went in mathematics, Hermann Weyl had been before. So he often expressed that kinship. And of course, Hermann Weyl himself had ventured into physics. He proposed a theory, the gauge theory, which was not right, but the idea of the gauge theory, of course, was fundamental. So this idea of being successful in influencing physics when they're not trying to, and then being slightly less successful when they're actually trying to do so, I think is something that they have in common. So with that view and that picture, I'd like to end my talk. I've gone on slightly too long, I apologize, but thank you for your attention.
So that was really interesting and enlightening. Thank you. So I'm sure everybody's anxious to go away and find their dinner. But does anybody have any quick comments or question they'd like to say, or everybody's already got their minds on other things? Yeah, okay.
It's one question, but it sounds like two, sorry. So Michael Atiyah used to often say that somehow he doesn't understand spinors. That spinors are a mystery, right? I'd like to know what you think he thought about that. But as a related thing, my impression, he wasn't that interested in supersymmetry.
He often wondered about that, but
you know why? So it's a related question.
So I think he till his death would have claimed not to understand spinors fully. When he gave talks about that. And one of his interests in this context was, to see what geometry could teach him. So I think that was part of the story. But I never heard him say, "I've understood spinors." I don't
but do you know why he was so mystified? What is it that he was trying to convey by this comment?
I think I'll throw that discussion open to.
Yes. I think you made one comment about why, in the early days, Hodge and Dirac were both in Oxford, why the link with the Dirac operator in geometry, why it wasn't made then. And I think he mentioned that somehow, because there's something somewhat exotic and out there about spinors, that that was one of the reasons why they didn't kind of latch on.
You have some comment about the supersymmetry part?
I never discussed supersymmetry, so with him, I don't have any recollection of why he's particularly interested. But he must have been. I mean, he must have seen it at many talks. But maybe he felt there was two things being paired, one of which he understood, the other one he didn't. So that.
Okay, on that note, let's thank Bernd again, and see you all tomorrow.